All right, welcome to Unit 2.1c. This is part 2 of 2, where we're exploring the first half of the second key question. How do we describe qualitatively and quantitatively what happens during dissolution? In part 1, we focus on the qualitative aspects. Here, we're going to focus more on the quantitative aspect. Before we begin, it's going to be helpful for us to just sort of review how do we make a solution. So when making a solution, the first thing you do typically you start out by weighing out your solute. Let's say our solute is copper sulfate, and we weigh out 1.5 grams of copper sulfate. And then the next thing we're going to do is we're going to add that to our volumetric flasks. Remember, volumetric flasks are a special piece of labware that are calibrated to a certain volume. And so we put our solute into our volumetric flask, and then we're going to add some solvent, which will be water. And we're not going to fill it up all the way up to that marker there, but just enough to sort of mix it and dissolve it. Once it's all dissolved, then we're going to add solvent to the meniscus. And once we have that, we have our 500 milliliters of our solution. So now the question is, well, how do we calculate the concentration of the solution that we just made? Remember, concentration is quantified by molarity, which is moles of solute over liters of solution. So because we weighed out 1.59 grams of copper sulfate, we can calculate the moles using its molar mass, and that's going to correspond to 0.01 moles of our solute. For the liters of solution, we just have to look at our volumetric flask. It's a 500 milliliter volumetric flask, which is equivalent to 0.5 liters. And so that gives us molarity is equal to 0.01 divided by 0.5, and that gives us the molarity to be 0.02 molar. Now, you could do this sort of backwards. Maybe you knew the molarity you wanted and the amount of solution that you wanted. So let's say you knew you wanted a 0.002 molar solution and you knew you wanted 500 milliliters of it. You would plug that information into your molarity equation, use that to solve for the moles of solute that you need. Once you have the moles of solute that you need, you convert that to mass to figure out how much solute you need to weigh out. But at any rate, this is sort of how we go about making solutions and calculating their concentrations. All right, so now let's look at an example where we're actually doing something similar to that. So we wanted to calculate the concentration of chloride ions in a solution made from 25 grams of barium chloride dissolved in enough water to make 200 molar solution. And the first thing I'm going to do is I'm going to write out the dissolution equation that corresponds to it. So if you take barium chloride and you dissolve it in water, it breaks apart into 1 barium ion and 2 chloride ions. And this is going to be helpful for my molar ratios. Then I'm going to solve it. But before I do that, I should map out my plan. So I'm starting with 25 grams of barium chloride, and I want to get to the molarity or the concentration of chloride. So since I'm going from barium chloride to chloride, which are two different things, I know this is going to be a stoichiometry problem. I know I'm going to need molar ratios, and that's what my balanced chemical equation is going to help me with. And because I'm going from grams to molarity, not from moles to moles, I know the mole map will also be helpful. So I have that up the top corner here. All right, once I have all that down, let's figure out how we're going to bridge this gap here. So we would go from grams to moles of barium chloride, and then from moles of barium chloride to moles of chloride, and then from there I can get my molarity. All right, what does this math look like? We have 25 grams of barium chloride. I'm putting it over 1 to make it into a fraction. I know some people are having this putting things like 1 moles here or 1 liters here. This should only be a 1 in this case because I'm only doing that to make it into a fraction, nothing more. So just a 1 in the denominator. Then I'm going to multiply it by this conversion factor, which comes from the molar mass. And notice that I have the grams are in the denominator here so that they can cancel out because they need to be opposite to cancel out. And this number, once again, is just the molar mass. All right, so now once I have that, I can go ahead and multiply by the conversion factor because I have moles of barium chloride. I want to get to moles of chloride. So I'm going to multiply by the conversion factor. And this information is going to come from the balanced chemical equation. Super important to note because I'm noticing some people are still making this error. The 2 in front of the chloride, I'm only using it here. I'm only using it to convert from moles of barium chloride to moles of chloride. This is only useful as a mole ratio. This 2 does not tell me how much I have. It also doesn't tell me how to calculate the molar mass of chloride, like none of that. I'm only using that 2 here. All right, so I have my conversion factor to go from moles of barium chloride to moles of chloride. And then once I have that out, I'm going to then, actually I have a choice of what I can do. So let me just back up. You could stop here if you wanted to and calculate the moles of chloride and then use that to plug that into the molarity equation to get the molarity. Or if you're using dimensional analysis, remember molarity is moles over liter. So that means the next thing I'm multiplying with should have liter in the denominator. That's where I want liters in order to get molarity, since it's moles per liter. All right, so then once I have that, I can go ahead and multiply out my numerators. 25 times 1 times 2 times 1 gives me the 50 on top, and then 1 times 208.23 times 1 times 0.2 gives me the 41.646 liters at the bottom. And when I do my math out, when I divide these two together, I get 1.2, and then moles divided by liter is just molarity. All right, you're now going to try a CFU that looks very similar to this one. If you get stuck during that CFU, do not just go ahead and press play. You want to rewind this video and see where in here that you get stuck. So sort of help you out. You really want to try it so that you know what you know and you know what you don't know. All right, so here's your CFU. Pause the video now. When you press play again, after you really try it, the answer will be revealed. All right, so here are some of the things that you should have for the CFU. That's the balanced equation for the dissolution of sodium phosphate. And you want to figure out from 9 grams of sodium phosphate, what's the molarity. So you want to go from 9 grams to moles of sodium phosphate to moles of sodium, and then to the molarity. Your work should look something like this if you're using dimensional analysis. And then you should get the concentration of sodium to be 4 molar. There's only one significant figure here because we're starting off with 1 sig fig. All right, let's look at another example. This example is similar to the ones we saw before. We're asked to calculate the concentration of chloride ions in a solution made by diluting 50 milliliters of 0.30 molar barium chloride to 78 milliliters. What that means is that we're starting with 50 milliliters of 0.3 molar solution, and we're adding enough water to get the volume to become 78 milliliters. So we're diluting it down. All right, so sorry about that. So we're going from 50 milliliters of a 0.3 molar barium chloride solution to, we don't know the molarity of a 78 milliliter chloride solution. And the mapping looks very similar. We're going from what we're starting with to moles of barium chloride, from moles of barium chloride to moles of chloride, and then from there we can get the molarity. So that part in the middle is the same as that we saw in example 1. All right, what about the work? If we're using dimensional analysis, I just want to note here, for molarity, whenever you're using molarity in dimensional analysis, you actually have to break it down into its fundamental units. Molarity is actually moles over liter. So in this case, we're going to take the 0.30 molar and make that 0.30 moles over 1 liter. Because this, if you did that math, that would be the same thing as 0.30 molar. Moles divided by liter will give you 0.30 molar. Notice here, I don't have it over 1, I have it over 1 liter of barium chloride. And this is the only time I would ever put a unit when I'm starting, is if I'm starting off with molarity, and that's because I'm breaking it down into its units. Other than that, typically the denominator for the first thing you're starting off with should just be 1, but not for molarity. This is where we use units in the denominator. Okay, so I want to get rid of liters to get moles of barium chloride. So since liters are in the denominator, I'm going to multiply by liters in the numerator here, and that will cross that out, give me moles of barium chloride. Once I have moles of barium chloride, I'll use the molar ratios to convert from moles of barium chloride to moles of chloride. And then once I have that, I would multiply by this fraction, where again, since I want to end up with molarity, and molarity is moles over liter, I will have the liter in the denominator, just so I can have molarity. So when I do my math out, that should look something like this. And that corresponds to 0.38 molar. Okay, you're going to try a similar thing with CFU4. If you get stuck, remember you're going to pause what you're doing and then rewind to see how it's done. You can choose to do this dimensional analysis as I did in my example, or you can do it stepwise where you're plugging things into equations one at a time. All right, so this is sort of what the work should look like, going from 10 milliliters of 2.10 molar solution, and you're trying to find the molarity of sodium. You want to go ahead and go to moles of sodium phosphate to moles of sodium, and then to molarity. And again, this is sort of what the work would look like using dimensional analysis. Maybe you choose to do something different. All right, and you should get a concentration of 2.5 molar. All right, so now with that being said, I'm going to show you a shortcut that will be helpfor a problem like example 2 or CFU4, where you're going from the molarity and volume of one thing to molarity and volume of something else. This is called the M1V1 equals M2V2 shortcut. So again, you can use this for when you're going from molarity and volume of one thing or the same thing to molarity and volume of something else or the same thing. All right, so, and it works because M times molarity times volume is equal to moles, and then the N and the N2 and N1 just takes care of the mole ratio. So let's take a look at an example where we're using it. This is example 2, same problem here. So to solve it, what I'm going to do is I'm going to start off with the molarity and volume as my M1 and V1. And here I have the mole ratios, and that comes from the balanced chemical equation. So N2 and N1 will come from the balanced chemical equation. I set my species 1 or substance 1 as my barium chloride, and so here's its molarity and its volume of barium chloride. And M2 would be the molarity of the chloride ion plus and the volume of the solution that I'm looking for. So this is sort of my initial, this is sort of my final. And then the barium chloride to chloride molar ratio is 1 to 2. So that means that the molar ratio for barium is 1 and for chloride is 2. And so that's what the N1 and N2 would correspond to. All right, so once I have that, I can just go ahead and plug that into the equation. And I would isolate for my M2 and I get 0.38 molar, which is the same thing that I've seen before. Same answer I got before. So the main thing here is to make sure you keep track of what everything is. I set the information for substance 1 to be barium chloride. So that means that the molarity and the volume was for my barium chloride solutions. That will be my M1 and V1, sort of what I'm starting off with. And that means that the mole ratio, my N1, would correspond for the molar ratio of barium chloride. Whereas 2 is for my chloride, so N2 would be the molar ratio for the chloride, since it's a 1 to 2 ratio. And last thing, you'll notice that in the equation, the N2 goes with the M1 and V1, and N1 goes with the M2 and V2. You just switch them up just to make sure that you take care of the mole ratios there. All right, here's your CFU. You're going to try it using the shortcut. When you press play again, the answer and work will be revealed. Great, so you have this equation here. You're just plugging everything in. You're starting off with 2.1 molar and 10 milliliters, and then you can go ahead and plug that into that side of the equation. M2 is what you're looking for, V2 was 25, you plug that in, and then of course you need to switch off the molar ratios for the sodium phosphate and the sodium. So N1 would be for sodium phosphate, and N2 would be for sodium, which is a 1 to 3 ratio. All right, so you should get the same answer, 2.5 molar. This is a very useful trick because you also don't have to convert. Notice you don't have to convert the volumes as long as you're consistent. If it's all in milliliters, it's totally cool. You don't need to do any conversion there. All right, I hope you all found this video helpful. That's it for this video. Have a quality day.